Linear diophantine equations. A linear diophantine equation is an equation of the form ax plus by equals to c, where a, b, and c are all integers. Let's say the GCD of AB is equals to D. If D divides C, then the diophantine equation can be solved. That is, there is a solution. If D does not divide C, it means there is no solution. Let's say we solve a diophantine equation. I will have the solution x equals to x naught and y equals to y naught. Then there exist many other solutions, or infinitely many solutions, which can be obtained by the general formula x equals to x naught plus b over t times t, and y equals to y naught minus a over d times t, where t is any integer. To solve a diophantine equation, we need to start by looking for the GCD of A and B, and then find out if this GCD can divide C. To look for the GCD of A and B, we need to carry out the Euclidean algorithm. That is, the greatest common divisor of A and B can be obtained by carrying out successive division of A by B. GCD also means HCF, highest common factor. You also know that A over B means A divided by B. And if A is divided by B, we can have the answer Q plus a remainder, which should be over the divisor B. Is the same like I have 5 over 2. I have the answer 2 and then the remainder 1. So, I have to put it 1 over the divisor, so that if I simplify this side, I am going to have back this other side. That is, 2 times 2 is 4, 4 plus 1 is 5, so which is the same like 5 over 2. Is the same here. Now, let's say we multiply the left hand side and the right hand side by b. We'll have A is equals to QB plus R. You also know that A here means the dividend, and what is dividing A is called the divisor, and the answer we obtain is always called the quotient, and R the remainder. To look for the greatest common divisor of A and B using the Euclidean algorithm, we follow the following steps. Let's say A divides B and we have the answer Q1. Then we can write A is equals to Q1 B plus remainder, let's say R1. In the next step, we bring B here is equals to R1. We bring R1 down here. R1 divides B. Let's say we have another question. Let's say Q2, and we have another new remainder R2. In the next step, we bring R1 here, and we bring R2 to be the new divisor. Let's say R2 divides R1. We have Q3 plus a new remainder. Let's say R3. In the next step, we bring R2 here and we bring R3 down here, which is now the new divisor. We divide R2 by R3, we have the new quotient, let's say Q4 plus the new remainder R4. This division can continue until we have, let's say, a remainder Rn. And then here we'll have Rn minus 1, and here we'll have Qn. It will be Rn minus 2. Let's say Rn was the last remainder, then we can continue. We have here Rn minus 1 will be equals to Qn plus 1 Rn plus 0. We stop when the remainder is 0. And if the remainder is 0, it means the GCD of A and B, GCD of A and B will be equals to Rn. That's the GCD will always be the last non-zero remainder. In this case is Rn. You also need to know that the remainders here can be gotten as R1 is equals to A minus Q1B, and here R2 is B minus Q2 R1, and so on. Example, find the general solution of the equation 1023x minus 924y equals to 33, where x, y are integers. To solve this equation, we start by looking for the GCD of 1023 and 924. If this GCD can divide 33, then there is a solution. If it doesn't divide 33, then there is no solution, and we will not solve the equation. The GCD of these two numbers can be obtained using the Euclidean algorithm. In the Euclidean algorithm, I write the bigger number on the left hand side of the equal sign and the smaller number on the right hand side. I divide 1023 by 924, that will be 1 time, plus the remainder. To get the remainder, that is R1, I'll take 1023 minus this product, 1 into 924, and I'm going to have 99. So the remainder here is 99. Now I bring this divisor here in the left hand side. That's the previous divisor, and the new divisor now will be the previous remainder. That's 99. 99 divides 924 9 times, plus the remainder, let's say R2, which I don't know. So R2 will be, that's R2 will be 924 minus 9 into 99, which is 33. I bring the previous divisor to the left hand side, that's 99, and now I bring the previous remainder here, which will now be the new divisor. 33 can go to 99 3 times, plus remainder 0. Since 99 minus 3 times a 3 is 0, 3 times a 3 is 99, so 99 minus 3 times a 3 is 0. Now we have arrived 0, so we stop. And then the GCD of 1023, 924 is the last non-zero remainder. In this case is 33. So the GCD of these two numbers is equals to 33. You see, now we see 33 can divide 33. 33 can divide 33. It means this equation can be solved. To solve this equation, we start from the GCD, which was 33, and we go backwards. That is 33 is equals to 924 minus 9 into 99. 99 is equals to 1023 minus 1 into 924. So here I'm going to replace 99. That is 33 is equals to 924 minus 9 into 1023 minus 1 into 924. Now I've reached the last level, so I stop, and I will try to arrange this equation to look like this. That's the original equation that I was given. Now 33 is equals to 924 minus 9 into 1023 plus 9 into 924. Here I have 1 924, and there I have 9 924. 1 924 plus 9 924 will give me 10 924. That is 33 is equals to 10 924s minus 9 1023s. That is 33 is equals to minus 9 into 1023 plus 10 into 924. You know, 1023 was the first term, and x was attached to 1023, so here is minus 9. So I arrange so that 1023 should be in front and minus 9 should be behind. So I have 33 is equals to 1023 into minus 9, and here I have minus, but here is plus, so it's the same like minus minus, because minus minus is plus, into 924 into 10. So I want to make sure that there's only one minus here as it is here. So I'll have 33 is equals to 1023 into minus 9 minus 924 into minus 10. So now I have only one minus between the two terms as here. If we compare this equation now with this one, I will see that x is equals to minus 9 and the y is equals to minus 10. Now x is equals to minus 9 and y is equals to minus 10 are some of the solutions of this diophantine equation. Let us call this solution maybe x naught is equals to minus 9, y naught is equals to minus 10. Other solutions can be obtained by the general formula x is equals to x naught plus b on d times t, where d here is the greatest common divisor and b is minus 924. That is, x is equals to minus 10 plus minus 924 all over 33 times t, which is the same like x is equals to minus 9 minus 28t. Since minus 924 divided by 33 is 28, so minus 28t. So this is one of the general solution. The general solution here can be given as y is equals to y naught minus a over d times t. That is, y is equals to minus 10 minus into a, which is 1023, divided by d, which was 33, times t. 1023 divided by 33 is 31. So y is equals to negative 10 minus 31t is another general solution for this equation. Another example, find the general solution of the equation 561x plus 323y is equals to 51, where x and y are integers. To solve this equation, we need to first of all look for the GCD of 561, 323 and find out if this GCD can divide 51. If it can divide 51, then there is a solution. And if there is a solution, then there are infinitely many solutions, which we can then obtain using the general formula. To look for the greatest common divisor, we use the Euclidean algorithm. And then in the Euclidean algorithm, we need to put, that's the bigger number, which is 561, to the left hand side of the equal sign. That is, 561 is equal to 323. 323 divides 561 one time plus a remainder. The remainder can be gotten by taking 561 minus this product, that is 1 into 323, which is equals to 238. So the remainder here is 238. Now I bring the previous divisor here, which is 323, and then I bring the previous remainder 238 here. 323 divided by 238 is one time. To get the remainder here, I'll take 323 minus this product, which is 85. I bring the previous divisor here as 238, which is equals to, and I bring the previous remainder here, that's 85. 85 divides 238 two times with a remainder. So the remainder here will be 238 minus 2 times 85, which is 68. I bring the previous divisor here, that's 85, and then I bring the previous remainder here, that's 68, can go to 85 one time, and then the remainder here is obtained by taking 85 minus this product, that's 68, which is 17. Now 68 is equals to 17 divide 68 4 times. 4 times 17 is 68. And to get the remainder here, I take 68 minus 4 times 17, which is 68, will give me 0. So from the Euclidean algorithm, when I arrive 0, I stop. And then the GCD of these two numbers will be the last non-zero remainder, which is 17. And you see, 17 can divide 51. It means this equation can be solved. To solve this equation, I start from the GCD here and I move backwards right to the first step. That is, 17 is equals to 85 minus 1 into 68. That is 85 minus 1 into 238 minus 2 into 85. Since 68 is equals to 238 minus 2 into 85. So I replace 68 here by 238 minus 2 into 85. Now the next step is 85 is equals to 323 minus 1 into 238. But I have two 85s here. To simplify my expansion, I need to make sure there is 185. That is 85 minus 1 times 238 plus minus times minus is plus 2 into 85. 185 plus 285 is 385s minus 1 238. I know 85 is equals to 323 minus 1 238. So I have to replace 85 here. So I'll have 3 into 323 minus 1 into 238 minus this 1 into 238 up here. That is 1 into 238. Now 238 is equals to 561 minus 1 into 323. But I'm having two 238. I'm having 238 in two places here. So I need to make sure that I should have 238 in one place. To do this, I need to expand and then I simplify. That is 3 times 323 minus 3 times 1, which is 3 into 238 minus 1 into 238. Minus 3 238 minus 1 238 is the same like minus 4 238. So I have 3 into 3 2 3 minus 4 into 238. Now 238 is equals to 561 minus 1 into 323. So I have to replace 238. So I have 3 into 323 minus 4 into 561 minus 1 into 323. 1 into 323. Now I have 323 into two places. I need to make it to be 1. So I need to expand and simplify. That is 17 is equals to 3 into 323 minus 4 into 561 plus 4 into 323. Since minus times minus is plus, 323 plus 4 323, it is 7 323. So it is the same like 7 into 323 minus 4 into 561. But here 561 comes first, so I need to rearrange it so that it should be the first term. That is minus 4 into 561 plus 7 into 323. Now I got minus 4 into 561 plus 7 into 323 is equals to 17. This equation was equals to 51, not 17. So it means I need to make the right hand side to be 51. You know, 51 divided by 17 is equals to 3. So it means if I multiply 17 by 3, I'm going to have 51. And if I multiply 17 by 3, it means I have to multiply all the terms in the left hand side also by 3. That is, I'm going to have 4 times 3 into 561 plus 7 times 3 into 323, which is equals to 17 times 3. That is minus 12 into 561 plus 21 into 323. Since 7 times 3 is 21, is equals to 51. Now the right hand side is 51. I have to rearrange this equation to look exactly like this. 561 is in front, so I need to put in front and I put minus 12 behind so that I should be able to compare. So now I have 561 into minus 12 plus 323 into 21 is equals to 51. These two solutions are one of the many solutions of this equation. Let's say this x here was x naught of the many solutions. Then the other solutions can be obtained using the general formula x is equals to x naught plus b over d times t. That is x is equals to minus 12 plus b here is 323 over d, which was 17 times t. That is x is equals to minus 12 plus 19t. Since 323 divided by 17 is 19. This is one of the general solution. Now for y naught is equals to 21. The other values can be obtained from the general solution. Y is equals to y naught minus a over d times t. Y is equals to 21 minus a is 561. 561 divided by 17 times t. That is y is equals to 21 minus 33t. Is another general solution. So the two general solutions are x equals to minus 12 plus 19t and the y equals to 21 minus 33t. To be able to continue to see new videos from any of these my channels, you need to subscribe to the channel and like any video that you see. Subscription is free. To subscribe, you come down to this subscribe icon and you click. When you see subscribe, it means you have already subscribed.